Good morning and welcome to this week's CEIA Maths tutorial for higher level Leaving Cert Maths. This week's session we're going to look at Trigonometry 3 and Complex Numbers Polar Form, and it's presented by myself, Adrian Williams. And before we start, I just would like to thank CEIA for facilitating and organising this programme of maths tutorials for higher level and Leaving Cert students. So let's start by taking a look at what we're going to cover in today's session. We'll have a quick welcome introduction, followed by a discussion on the unit circle. Now, I do tend to go on a lot about the unit circle, but that's because of my experience working with Leaving Cert students over the last number of years. I feel that time spent on refamiliarizing ourselves with the unit circle is usually time well spent. After that, we'll have a quick break for 5 minutes and we will move on to complex numbers polar form. That'll take about 40 minutes, followed by another quick break. And then finally, the last maths topic for today will be trigonometry 3. And after that, if we have time and you're still willing to listen to me for a little while longer, I'd like to share some tips and ideas or advice for revision and preparing for Leaving Cert higher level maths course and exams. So by way of introduction, I just want to share briefly my own history and journey through third level education and follow-on career. I sat my Leaving Cert exam in 1986 and had an interesting journey through the CAO process, and unexpectedly found myself starting a course in industrial engineering in what was then UCG, now NUIG. I found the course interesting, and as well as the core modules that you would expect from engineering as maths and physics and so on, we did a wide variety of other modules that I found interesting. I can remember studying things like physiology, economics, accounting, organizational change, but two modules in particular really interested me, and they were programming and manufacturing support or manufacturing management systems. And I felt that they were very complementary modules, and that my guess had been that there was quite a good job market for people with that knowledge and those skills, and that professionals with that knowledge and skills could be quite well paid. And it turns out I was right. And after an engineering degree, I did a postgrad in systems analysis, and shortly got a job in a manufacturing firm as a manufacturing business analyst. And I have been doing that in one shape or form ever since. So in a very real sense, the knowledge and skills I picked up in the engineering course have given me my career ever since. And not only that, but I met my wife in college, and so I also have to thank UCG engineering course for that. Regarding maths, I have to say that I don't particularly use maths in my career. Possibly the only or the closest thing that I would use in my career that is in the Leaving Cert course would be financial maths, something like that. So really nothing more complicated than addition, subtraction, multiplication, division. But my wife actually is a maths teacher, and the Department of Education introduced Project Maths in 2010, and so all maths teachers required training on that. And while my wife was being trained on that, she was sharing her experience of the introduction of Project Maths, and I found that interesting. And then shortly after that, I was asked by a number of students if I could help them with, certain topics that they were struggling with in the higher level maths course, and I agreed. And it kind of snowballed a little bit, and over the last 6 to 8 years, gradually I've relearned the higher level Leaving Cert maths course, and I found it fascinating the second time around. And I've also become very interested in how students learn maths and how they revise maths and prepare for and keep this wide body of maths knowledge in their head long enough to sit the exams. And that's something that I've become very, very interested in the last number of years. Hence my spiel about the tips and advice at the end of today's session. Okay, so that's enough about me. Let's get started. Let's go and take a look at the unit circle. Okay, so today I'd like to start by looking at the topic of the unit circle. Now, the unit circle is a very simple topic, and it's probably something that you were introduced to at the very beginning of your senior cycle maths program, maybe at the beginning of the trigonometry chapter. So maybe because the unit circle topic is so simple and students don't really feel the need to continually revise it as they move through the senior cycle. So it's often the case that by the end of the senior cycle, a lot of students have forgotten about the usefulness and relevance of the unit circle topic as a tool for working with and solving problems in trigonometry and complex numbers polar form. So for those students, I think it's worthwhile revising the topic of the unit circle. Now, if you're not one of those students and you are a big fan of the unit circle and use it for solving many problems in trigonometry or complex numbers, then you might want to skip this section or go and have a cup of tea. But if you're curious about, maybe you remember studying the unit circle, but you can't quite remember how it fits in or how you can use it as a tool for solving these problems, then bear with me. So what is the unit circle? Well, first and foremost, it's just a circle. It's set in the XY coordinates with the center of the circle at the origin 0, 0. And most importantly, the radius of this circle is 1, hence the name unit circle. Now, at the center of the unit circle, there is an angle taken from the positive x-axis in an anti-clockwise direction, and angles are always described in that way, unless otherwise specified. From the positive x-axis in an anti-clockwise direction, and this angle t, when it strikes the unit circle, there is a point, and if we look at that point in terms of the xy coordinates, it forms a horizontal distance along the x-axis and a vertical distance along the y-axis. And the point about the unit circle is that the horizontal distance made by where this angle strikes the unit circle is actually the cosine of the angle t at the center of the circle, and the vertical distance where this angle strikes the unit circle is equal to the sine of the angle at the center of the circle. So this is quite easy to prove using SOHCAHTOA. So just using a right angle triangle, taking sine for example, the sine of angle t will be the opposite over the hypotenuse. Okay, so just rearranging this equation, the opposite will be hypotenuse multiplied by sine t, but in the case of a unit circle, hypotenuse equals 1, therefore the length of the opposite side in a unit circle equals sine of the angle at the center of that circle, or sine t is equal to the opposite or vertical side along the y-axis. And similarly, we can prove that cosine is equal to the adjacent or the horizontal distance along the x-axis. So that's the basic message that I want to get across about the unit circle. Let's move on. Before we go on to talk about radians, I just want to introduce you to a tool called GeoGebra, and we're going to use it to just look at some lessons about the unit circle. So GeoGebra is a really good tool to help understand and demonstrate ideas and concepts in maths. It's freely available on the internet, although a lot of the time the lessons don't run very well on Internet Explorer, so maybe use browsers such as Edge. Okay, so we want to look for GeoGebra lessons relating to the unit circle, so I'm just going to Google GeoGebra unit circle and pick up the first link, which is actually from the GeoGebra org itself, unit circle GeoGebra. Okay, and it gives us a load of different books all relating to the topic within GeoGebra, all relating to the topic of the unit circle. I'm just going to pick the first one, trigonometry and the unit circle. And within that, then I have 5, I suppose, lessons. And I'm going to pick the first one in the corner. And what we get is this simple GeoGebra lesson all about the unit circle. Okay, so it's quite a simple one. We have something here called a theta slider, and we have to move the theta slider to investigate unit circle values. And this is the slider here. So by moving the dot back and forth along the slider, we can change the angle at the center of this unit circle. And we just use this to see the relationship between the changing angle at the center of the circle and the corresponding values of cosine and sine theta relating to that angle. Okay, so these are, the horizontal and vertical distances of where this angle strikes the unit circle. Okay, and we can just see as we increase the angle from 0 to 90 degrees, the value of cosine is decreasing and the value of sine is increasing. And if it's kind of difficult to get exactly on 60 degrees on specific angles, but if you can get it on 30 or 45 or 60, you can see exactly maybe some cosine or sine values that we would recognize, well, especially in this case cosine values. So at 60 degrees we can see that the cosine of the angle, the cosine of 60 degrees is 0.5 or half. And you can clearly see that this distance here is about half of the distance from 0 to 10 on the unit circle. So we can accept that. Okay. And you can just play and change the angle up and down, and you can see that the cosine is decreasing and sine is increasing. And this is the first quadrant. And you can move into the other quadrants then. So in the second quadrant, we notice that as the angle gets bigger and bigger and bigger, cosine begins to increase again in terms of magnitude, at least until we get to 180 degrees, where cosine will be -1 and sine will be 0. But the point about the second quadrant is that cosine moves from the positive x-axis to the negative x-axis. So all angles in this quadrant will have a negative cosine, and a positive sine. Okay, so that's useful to know. So in this quadrant, both cosine and sine are positive. In this quadrant, cosine is negative and sine is positive. As we move to the third quadrant, and just keep increasing the angle by moving the dot along the slider. Now, in this case, both cosine and sine are negative. So, in our unit circle, this is the negative y-axis, this is the negative x-axis. So all angles in this quadrant have both negative sine and negative cosine. And then finally, moving to the last quadrant, cosine moves back into the positive x-axis again. So we can see any angles, this would be like from 270 to 360. All angles in this quadrant have a positive cosine and a negative sine. So this is just, it's kind of a tool to play with, I suppose, to just help you understand the relationships between the angles and the values of cosine and sine of those angles. So that's it. That's all I wanted to show you. Okay, before we go on, I want to talk about radians. And I want to check what is your understanding of what is radian. And we're going to do a little multiple choice quiz to see what people think. So what is a radian? Is it a unit of measure of angles? About 57.3 degrees. 180 degrees divided by pi, or the angle subtended at the center of a circle by an arc equal in length to the radius. Have a think about it. Okay, what answer did you get for the question, what is a radian? Well, the good news is all the answers were correct, so no matter which answer you picked, you were right. Definition of a radian is, it is indeed a unit of measure of an angle. It is equal to about 57.3 degrees. It is equal in degrees to about 180 degrees divided by pi. But the best answer is that it is equivalent to the angle subtended, that's a strange word, subtended at the center of a circle by an arc equal in length to the radius. Now that sounds a little bit complicated. Let's just try and understand it in a little bit simpler terms. So if you can imagine an arc around a circle where the length of the arc is the same as the radius, and I don't think it's any accident that the word radian and radius are very, very similar. So imagine an arc where the length of the arc is equal to the radius. Now imagine that angle at the center of the circle giving us that arc. Well, that is equivalent to 1 radian. So we can say that 1 radian is the measure of the central angle whose arc length is the same as the radius of a circle. So an interesting thing about radians is that radians give us pi, and actually not vice versa. So if we look at a semicircle, which we know to be 180 degrees, but in terms of radians, how many radians are in a semicircle? So again, radian is defined by an arc of length equal to the radius. So 1, 2, 3, and a bit times. So in other words, if you look at the arc of a semicircle, that's equal to 3 and a bit times the radius of that semicircle. And the bit is 0.14159, blah, 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 blah. It goes on forever. So pi is defined by the number of times the radius can be divided into the arc of a semicircle. Okay, so we've talked about the unit circle, and then we've talked about radians as a measurement of angles. And I'm afraid the bad news is you really need to get familiar with using radians as a measure of angles as opposed to degrees. Maybe you've always used degrees and you're very happy with them. Well, you really need to begin to be comfortable with and use radians as a measurement of angles. So putting the two together, degrees, radians, and the unit circle together, we come up with this kind of scary picture here. And this is basically still, it's the unit circle, set in the XY coordinates, center 0, 0, and radius of 0 to 1. But now we have marked off actually 16 angles within that unit circle. And each of the angles we have described in both degrees and in radians. So let's just look at this for a minute. Okay, so we saw on the last slide that in a semicircle, we have pi radians. Okay, remember how it was described. So pi radians in 180 degrees. So in 90 degrees, we would expect pi over 2 radians. Okay. For 60 degrees, which goes into 183 times, it would be pi over 3. 45 degrees, pi over 4, and then 30 degrees, pi over 6. So that's kind of easy enough to understand, at least in this quadrant. As we move to the other quadrant, it becomes a little bit more difficult. So we have to think of 120 as 60 plus 60. So that's sort of pi over 3, 2 pi over 3, 3 pi over 4, 5 pi over 6. So get used to thinking of these angles 120, 135, 150 in terms of pi rather than in terms of radians rather than degrees. Okay. And then similarly for this quadrant, 210 degrees is equal to, it's like 180 plus 30. So that's like pi plus pi over 6. So that's equal to 7 pi over 6. And so on in 270 degrees, it's pi plus half of pi, so 3 pi over 2, and on back to 360 degrees. So in this representation, we're showing actually 16 angles within the unit circle. Okay, I don't know if there's a name on these. I'm just going to call them angles of interest because for the purposes of complex numbers polar form and this section of trigonometry, we tend to just deal with these kind of 16 angles, 30, 45, 60, 90, 120, 135, all the way around to 2 pi or 0. And so I'm just going to call these angles of interest, okay? And for each of these 16 angles of interest, we need to be able to understand and recognize them in terms of radians. Okay, pi over 6, that's great. But also, if you just look over here to the right of each angle in this diagram, we're seeing coordinates actually. Root 3 over 2 comma a half, and these are actually the coordinates again, as we saw at in the first picture of the unit circle. These are the coordinates of this point, given that this is the unit circle set in the xy coordinates with the center of 0, 0 and radius of 1. So this is actually the coordinates, horizontal coordinates of root 3 over 2 horizontally plus a half vertically. And what we saw in the first lesson about the unit circle is that these are equal to the cosine and the sine of this angle, which is 30 degrees, which is pi over 6 radians. Okay, so this diagram shows us, basically it gives us everything relating to the unit circle that we need to know. For each angle, what are the coordinates, and therefore what is the sine and the cosine, or the cosine and the sine of the angle at the center of the circle. So for pi over 6, we're seeing cosine of pi over 6 is root 3 over 2, sine of pi over 6 is a half. Moving on up to 45 degrees, which is pi over 4 radians. Cosine of pi over 4 radians is root 2 over 2, and sine of pi over 4 radians is root 2 over 2. For pi over 3 radians, it's a half, and you can imagine dropping this point down to the horizontal axis. It's about halfway between 0, 0 and 1, 0. So yeah, we can accept that coordinate should be a half root 3 over 2, which is, so we are saying cosine of this angle, pi over 3 radians, is a half, sine is root 3 over 2. Okay, and then on to 90 degrees, that's an easy one. Cosine is 0 and sine is 1. As we continue around the circle, then we looked at this in GeoGebra on the unit circle, but just to hammer home the point, now we are looking at 120 degrees. And the thing to notice about 120 degrees is that it strikes a point at the same height on the unit circle as 60 degrees. So the vertical distance of the two angles would be the same. So we can see that the y coordinate, root 3 over 2, is the same in both cases. In the case of the x coordinate, the horizontal distance, it's the same distance in both angles, but this is the positive x-axis and this is the negative x-axis. So the coordinates we have is minus a half root 3 over 2. Similarly with the 135, which is essentially 90 degrees plus 45 degrees, we have these coordinates of minus root 2 over 2 and root 2 over 2. So again, the vertical distance for 45 degrees and 90 plus 45 degrees is the same. The horizontal distance is the same, but this is positive and this is negative. So, we're seeing a pattern that in this quadrant, all the vertical distances are positive, but all the horizontal distances are negative. As we move down to this quadrant, as you would expect, it's the negative y-axis and negative x-axis down here. So both coordinates are negative, but we can see the same kind of pattern. So if you look at, for example, this angle here, 225, which is like 180 plus 45, then for 45 degrees, it's root 2 over 2, comma, root 2 over 2. Down here, it's minus root 2 over 2, comma, root 2 over 2, minus root 2 over 2, and so on. And then finally, in this quadrant, we're back into positive x-axis territory, but negative y-axis. So the x coordinates are positive and the y coordinates are negative, but it follows the same pattern. You can recognize the same coordinates for this angle here, which is 315, which is 270 plus 45 degrees. And so you can begin to see a pattern on the coordinates. So actually, although it looks like a scary picture with all these numbers around the outside, if you just take the first quadrant there and just change the signs, you can get the coordinates of angles in the other three quadrants. Okay, so we're coming to the end of our discussion on the unit circle. So we were just looking at this kind of scary picture with the unit circle with all the angles described in degrees and radians, and then for each angle we were looking at the coordinates of where those angles strike the unit circle, the x and the y coordinate, and what we're saying is they represent the cosine and the sine of the angle at the center of the circle. Okay, and you know, we noticed that the values are very much repeated as we work our way around the circle. So, for example, for pi over 6, we're looking at cosine sine of root 3 over 2, comma a half, whereas 5 pi over 6, it's minus root 3 over 2, comma a half. So the values are very much repeated as we work our way around the circle. Root 2 over 2, comma root 2 over 2, and that could also be written as 1 over root 2, comma 1 over root 2 if you wish. And then for 60 degrees, cosine of a half and sine of root 3 over 2. And again, that's very, very similar to what we're looking over here at, an angle of 2 pi over 3 radians, cosine of minus a half, sine of root 3 over 2. Now, the good news is that you don't have to try and remember all of these coordinates and values for sine and cosine and sine for all these 16 angles. You don't have to remember them or learn them off by heart for the exam. They're already in your logbook. So if you go to your logbook on page 13, there is a page dedicated to this topic, and it has, for example, it has a picture of the unit circle and shows quite clearly that you have an angle at the center of the circle where that strikes the unit circle. Well, the coordinates at that point are equal to cosine A and sine A of the angle of the center of the circle. Okay, but it also has all these values here that we were just looking at. And these are what we really want to get out of all of this. If you have an angle, we want to know, what are the cosine and sine values for that angle at the center of the circle. So we have a table here, and in the table we can see a number of angles listed in degrees, first of all, but also in radians, and we want to talk about radians from now on, really. Okay, and let's just see how this table here links up to this picture here, or let's just understand how that happens. Okay, so let's take the first angle, so 0 degrees, or 0 radians. So it's saying here that at 0 radians the cosine is 1 and the sine is 0. So we're expecting the coordinate of the point where that angle strikes the unit circle to be 1, 0, and there it is. That's fine. Let's skip pi over 2 pi and 3 pi over 2 for just a minute, and we'll go on to pi over 6 radians, or 30 degrees. So in our diagram here, we can see 30 degrees, pi over 6 radians. Okay, and the diagram here says that the cosine should be root 3 over 2, and that is what we're seeing in the table as well, root 3 over 2. And the sine should be a half, and that is indeed what we're seeing here as well, a half. Okay, so we can see that the information here is already in the table. Let's go on to the next one, pi over 4 radians, or 45 degrees. So here we have our angle here, pi over 4 radians on our unit circle, and in this picture here we can see that the cosine and sine are both listed as root 2 over 2. And in our table here, we can see they're listed as 1 over root 2 and 1 over root 2, which is actually the same as root 2 over 2 and root 2 over 2. Okay, whichever you prefer. Root 2 over 2 equals 1 over root 2 because you can cancel root 2 above and below the line. Moving on to pi over 3 radians. Here we have it here. So the unit circle diagram says that the cosine is a half and the sine is root 3 over 2. Okay, so everything that's here is in this section of the table, which is great. That's 3 of the 16 angles that we're talking about. Well, 4 if you count 0. Unfortunately, all 16 of these angles of interest aren't listed nicely and neatly in this table for us, but we can deduce them, I guess, using just these values here. So moving on, we can see we have 90, which is 0, 1, 0 and 1. That's pi over 2. Pi radians, minus 1, 0. Minus 1, 0. 3 pi over 2 radians, 0 minus 1, which is what we have here. Now, and then that's those covered. So let's look at some of the angles in the other quadrants, such as 2 pi over 3. Okay, so as we can see, 2 pi over 3 isn't listed as an angle in here. So what we've got to do is figure it out using the information we have here. So remember we talked about before, like 2 pi over 3, it's similar to the pi over 3 angle in that the horizontal distance out will be exactly the same. It'll be a half in both cases, but this is in the negative x-axis, whereas this is in the positive y-axis. So for pi over 2 pi over 3 radians, we will be expecting the cosine and sine values to be similar to what we have here, but we will be switching the sign of the cosine, so to be minus a half and root 3 over 2, which is what we have up here. Let's take another example, maybe perhaps down here. So 5 pi over 4, we need to recognize that that is similar to the pi over 4 angle. Pi over 4 gives us 1 over root 2 and 1 over root 2, but because of the quadrant that it's in, both those values will be negative. So cosine and sine of 5 pi over 4 would be minus 1 over root 2 minus 1 over root 2. And you remember we have this, I don't know if you use ACTS or CAST to help us remember which of the cosine, sine, tan are positive in which quadrant. So in this quadrant, both cosine and sine are positive. In this quadrant, only sine is positive. In this quadrant, both cosine and sine are negative, and in this quadrant, just cosine is positive. So using your knowledge now of the unit circle, comparing angles in these quadrants with angles in the first quadrant, you can use this table to quickly and easily get to values for cosine and sine of all of these angles in this manner. And this is basically the power and the relevance of the unit circle. And we'll go on to look at some examples of how to do that now in a minute. Okay, that's really all I want to say for the topic of the unit circle. Now, later on, I hope to spend a few minutes just going through some ideas or tips or advice that you might or you might not like to think about trying for your own preparation for the higher level Leaving Cert exam. One of the things I like to use is something called a checklist. And the idea of a checklist is it's a list of small tasks or key maybe questions that test my own understanding of key elements of the topic that we've just studied. So this is something that you might like to prepare directly after finishing a particular topic in class or in school or in your own study. And the idea is that you keep this checklist in a folder or somewhere, and periodically pull out the checklist and test yourself on it to check that you still know how to do these core skills. And the idea would be that if you do this periodically, maybe once a month or something like that, it's not intended to take a long time, but the repetitive nature of testing and retesting yourself on some of these core skills relating to this topic will help keep it current in your head, and therefore when it comes time for revision for Christmas, summer, or the big day, the topic is not completely alien to you anymore. So this is a checklist I prepared for the unit circle, and I just simply have 4 topics on it. And you can see that some of them are quite simple. Be comfortable working in degrees and radians. Suggest you use radians unless asked otherwise, and extending the unit circle to a non-unit circle. Just bringing this to mind again very briefly. But there are 1 and 2 are actually exercises that you need to do yourself, and the checklist should include the question and the answer, so that and it's not intended to be a long test. It's supposed to be literally 10-15 seconds. Can you still answer this question or not? And if you can't, then maybe you need to do a little bit more revision on this topic. But hopefully through constant and periodic revision, these kind of skills that you need to be able to do coming out of the unit circle topic should become second nature to you. So we're going to go ahead now and look at 1 and 2 and see how do we do these. Okay, so let's look at the first question on our unit circle checklist. And that is, given an angle theta, find values for cosine theta and or sine theta without using your calculator. So the idea is that we would be able to solve this using our knowledge of the unit circle, which you remember, and the maths table page 13, which you will have with you in the exam. So the angle we're going to look at is theta is equal to 5 pi over 6 radians. So I'm going to give you a minute to see if you can, using the maths table, find values for cosine and sine of this angle. Okay, how did it go for you? Okay, let's go through the example. So we want to find cosine and sine of an angle 5 pi over 6 radians. And the first thing how I approach these kind of problems is I look at, well, 5 pi over 6, that's like pi minus 1 pi over 6. And I visualize a circle that looks like this, a unit circle that looks like this. So I have here my angle pi over 6, okay. And I imagine an angle then that is like pi minus pi over 6, which would be this one. And so I can visualize that the vertical distance of this point is the same, sorry, the horizontal distance of this point is the same as the horizontal of this point, except that it is negative. And I can visualize that, both of them are, above the x-axis and the same distance above the x-axis in the vertical distance. So I can visualize that 5 pi over 6, the coordinates of this point will be very, very similar to the coordinates of this point, except that the sine of the cosine value will be negative. Okay, so using this information, I can go to this table and I can look for pi over 6, and read from the table. I can see that for pi over 6, I get a value of cosine is equal to root 3 over 2, and sine is a half. So I'm expecting that the cosine and sine of 5 pi over 6 will be minus root 3 over 2 a half. And that is exactly what we have here. So that's just a quick demonstration on how to use the maths tables to solve cosine and sine values for any of our angles of interest. So let's look at the second question on our unit circle checklist. So question number 2, given a value for cosine of theta or sine theta, find value or values for the angle theta. And we're going to go through this method now, and the example we're taking is sine of theta equals minus a half. So we can imagine a unit circle, and we're putting in here sine of theta equals, starting off with a half, okay? And we're going to use the table on page 13 of our maths tables to understand what this means. So when sine of theta is equal to half, I can go to my maths tables, go sine of theta, look for a value of a half along here. Oh, there it is. And I can tell that the angle an angle for this would be pi over 6. So I can imagine a unit circle now. Sine of theta is equal to plus a half. Oh, okay, the angle could be pi over 6, but there can be two angles because there are two points on the unit circle where the vertical distance along the y-axis is equal to half, and that is at pi over 6 or 30 degrees, but also at this point here, and we can think of this point as being pi minus pi over 6, which is equal to 5 pi over 6. Okay, so the 2 points where sine of theta equals half can be pi over 6 and 5 pi over 6. But we weren't asked for the angles where sine of theta is equal to plus a half. We were asked for where they are minus a half. So again, we go back to our understanding of the unit circle. We think about, well, okay, there's plus a half, there's minus a half, right? So from our knowledge of the unit circle and using this table to the best extent possible, we can imagine, okay, so at minus a half, that also hits the unit circle at two different points, there and there. And given that, well, if it's plus a half, this angle is pi over 6, we can see that, okay, at minus a half, this angle here is pi over 6, or 2 pi minus pi over 6, which is like 11 pi over 6. But the other place that sine equals minus a half hits the unit circle is here, and that we can think about this as pi plus pi over 6, or 7 pi over 6. So our answers are theta is equal to 7 pi over 6 and or 11 pi over 6. And it's important to remember that there are usually two answers to questions like this. And it's probably a good idea to give your answers in both radians and degrees unless asked otherwise. So that's our unit circle checklist, and the idea is that at the end of the topic you think about and create some questions to test yourself on core skills or core ideas in the topic that you just studied. Give yourself, relatively difficult examples of questions and include the answer. And the idea is that from time to time you can periodically put out the check sheet and test yourself on these, and hopefully you will continue to be able to answer the questions 1, 2, 3 months after you initially studied the topic in class. And hopefully that you won't have completely forgotten and lost these core skills when it comes time to revise for your Christmas or summer or Leaving Cert exams. Okay, that concludes our discussion about the unit circle. I may have labored the point a bit much about the unit circle, but my feeling is that if at least some of you get a better appreciation of what the unit circle is and what it can do to help you in your journey through Leaving Cert Maths, then I think the time has been well spent. Let's take a quick break, 5 minutes, and we will come back here, meet back here in 5 minutes and start our discussion on complex numbers polar form. So let's pause for now. Okay, let's restart and we will start to look at complex numbers polar form. So now that we have talked about unit circle, I'm hoping that our journey through complex numbers will be a little bit quicker and easier. Now, in the last section, we talked about check sheets as a study aid tool that you might like to think about using. Another tool that I like to use is something called a summary sheet. And a summary sheet is, as the name suggests, simply one sheet of paper. And the idea is that while you are studying a topic in class or directly at the end of a topic studied in class, that you simply list the components of that topic, the bits and pieces that you will need to remember relating to that topic in class. So it's kind of just really a list to bring to mind what are the components, what are the subtopics, or the various elements within the chapter or topic that you have just studied. And the idea is that it just helps you remember, and it's a list of the bits and pieces that you need to familiarize yourself during revision. So I'm just showing you an image of the summary sheet I had prepared for complex numbers. Now, I understand that you had covered half of the complex numbers topic in an earlier session. That's Cartesian or rectangular form of complex numbers. So for today, we're going to look at the topics relating to the polar form. So we have the polar form itself, what is it? And then also following on from the polar form of complex numbers, we need to think about, and I will introduce you to de Moivre, and then finally applying de Moivre to find complex roots. So those are the topics within the complex numbers that we'll be looking at now. I had also prepared a check sheet for the complex numbers topic. And remember, we saw use of the idea of a check sheet in the last section for the unit circle. Basically, check sheets are kind of a list of tasks or sample questions that I can pull out from time to time, attempt the questions, and hopefully verify that I still understand how to do these specific core kind of tasks or questions in the topic. So this is the check sheet I'd prepared for the complex numbers topic as a whole, and I've highlighted the bits and pieces that we will need to be able to do for the polar form of complex numbers. So let's just go through what they are. First and foremost, it is essential that we be able to do conversion from the Cartesian form of complex numbers to the polar form, and from the polar form to Cartesian form. And there is some samples in the check sheet that we can use to test ourselves. Following on from that, we need to be able to use de Moivre to solve large powers problems. So the example I have here is 2 root 3 minus 2i to the power of 6. And then finally, using de Moivre to find complex roots. Okay. So let's get started, and we'll take a look at conversion from Cartesian to polar form. So the first thing we want to be able to do is convert Cartesian complex numbers to polar form. So let's remind ourselves a little bit about what complex numbers look like. So this is a typical complex number, and complex numbers are usually denoted by the letter z. So a typical one we have here is z is equal to 1 plus root 3i. And complex numbers are often represented in what's called an argand plane and this is called an argand diagram. And the argand diagram has two axes. On the horizontal axis is real numbers, and on the vertical axis is imaginary numbers. So this is a very, very typical complex number represented in Cartesian form. Now, if we want to look at the same complex number represented in polar form, it would look like this. Now remember, this is exactly the same complex number. Here is the complex number we're looking at, the point we want to get to. But in polar form, instead of defining this point as a distance out from the origin on the real axis and up from the origin on the imaginary axis, instead of defining it in terms of those distances, this in the polar form, the same complex number is defined in terms of an angle from the real axis and the distance from the origin. Now, some notation to note here that the angle from the real axis is often called, represented by theta in this case, is often called the argument, and the distance from the origin is often called the modulus. So what we want to be able to do today is take this complex number in the Cartesian form, this form, and convert it to a form that looks like this. Z is equal to the modulus, times cosine of the argument plus I sine the argument, close brackets. So the conversion process is the three-step process. We're going to go through it now. So step one of the process, starting with your Cartesian form, is to use Pythagoras to get the modulus of the complex number. So the modulus is the distance from the origin to the complex number itself. And you can see here that we have a rectangle. So we can get the distance from the origin to the complex number simply by using Pythagoras. So in this case, we get the modulus, r is equal to the square root of 1 all to be squared plus root 3 all to be squared. So that gives us the square root of 4. So the modulus in this case is 2. Step 1 done. Step 2 then is to rewrite the complex number in this form into taking the modulus outside of the bracket. So we start with z is equal to 1 plus root 3i, and then we take the modulus outside the bracket, so we end up with z is equal to 2 by a half plus root 3 over 2i, close brackets. Okay. The final step then goes back to our earlier experiences with the unit circle and using the table in the relating to the unit circle in the maths tables. And what we need to do is to use this table to find out, using these values for cosine of the argument and sine of the argument, to find out what the argument is. So effectively, what step 2 has done is to give us values inside the brackets equating to a unit circle. So we're back to our favorite topic from the beginning of today's session of the unit circle. So what we need to do is to look at these values and use the table here to find out what is the argument. So we want to find an angle whose cosine is a half and whose sine is root 3 over 2. So we go to the table on page 13 and we look at, say, starting with the cosine row. What we need to find is an angle with a value of a half. So yeah, we found one here. And also you need to find an angle with the same angle with value sine value of root 3 over 2, and that's here. So we have found our angle in this case, and in this case it is pi over root 3 radians. So we can complete step 3 of the process by simply putting in pi over root 3 as the argument. So the answer is z is equal to 2, the modulus, open brackets, cosine root 3 plus I sine root 3, close brackets. So we also want to know how to do the reverse, that is converting polar complex numbers to Cartesian forms. So let's reverse the process that we did in the last slide and convert z is equal to 2 times cosine pi over 3 radians plus I sine pi over 3 radians to Cartesian form. So it's basically a one-step process. You use the tables on page 13 of your maths tables to get a value for cosine pi over 3 and sine pi over 3. So in radians you find pi over 3 and substitute in for cosine pi over 3, substitute in a half, and for sine pi over 3, substitute in root 3 over 2. And then it's just a matter of multiplying this out to get z is equal to 1 plus 3i. Very, very simple process, but make sure you know how to do the conversion of complex numbers in both directions, from polar to Cartesian and also from Cartesian to polar. Okay, let's try an exam question based on what we've learned so far. So the question we're going to try is from the 2019 paper, higher level leaving cert, paper 1. And the question is 5B1. So v is a complex number. It's equal to 2 minus 2 root 3I. And we're asked to write v in the form, in polar number form, basically, r by cosine theta plus I sine theta, close brackets, where r is an element of real and theta is in the range of 0 to 2 pi. So for the question, I'm going to give you the 3 steps we just talked about to perform this conversion from polar form to Cartesian, and the tables that you would have in your maths tables during the exam. So give it a go, see how you get on. Okay, how did that question go for you? Let's go through it. So I have included here the 3-step process for converting Cartesian to polar form. Step 1 is to use Pythagoras to get the modulus of the complex number. Now, I'm not sure if I mentioned this before, but the modulus of a complex number v can often be written with the complex number with a bar on either side of it. So that just denotes the modulus of the complex number. Okay, so the modulus of the complex number v is simply if we have a complex number which is 2 minus 2 root 3i, we're using Pythagoras, so it's the square root of 2 squared plus 2 root 3 all to be squared, which gives us the square root of 4 plus 12. The modulus of v is equal to 4. Step 1, done. Okay. Step 2 is rewrite the complex number, taking the modulus outside of the brackets. So we're looking to convert the complex number into a form of modulus, open brackets, something plus something I, close brackets. Okay. So step 2, v is equal to 2 minus 2 root 3i. So we want that in the form of 4, open brackets, something else. Now, I find that the best way to avoid making simple arithmetic errors at this point is simply take the elements from here and divide them by whatever you're multiplying outside of the brackets. So 4, open brackets, 2 over 4 minus 2 root 3i over 4. And that's probably the most the safest way, really, to make sure that you don't make a silly arithmetic mistake in the heat of the exam hall on the day with all the stress and stuff attached to that. So then we can simplify that down. So 2 over 4 is 1.5, and that ends up being root 3 over 2i. Step 2, done. And then the final step is to find the argument associated with the complex number using our knowledge of the unit circle and maths tables. Okay. So at the end of step 2, what we've basically done is what's inside the brackets is in kind of a unit circle form, where the first coordinate is the cosine of the angle and the second coordinate is the sine of the argument of this complex number. And what we need to do now is to use this information and the maths table to find out what is the argument. Okay, so we have a cosine of a half and a sine of minus root 3 over 2. But we don't let's start. So for cosine, we're looking for an angle whose cosine is a half, and we look along the cosine line and we find them right here at the end. Oh, here we have something an angle whose cosine is a half, and then double check. We want also the sine of the angle to be minus root 3 over 2. Now there's no root 3 over 2 here, but we have at the end again root 3 over 2 plus root 3 over 2. So we know that the angle we're dealing with is similar to pi over 3 radians. Okay. Now, given that the cosine is positive and the sine is negative, it means we're talking about something in the fourth quadrant where cosine is positive and sine is negative. Now, in the first quadrant where the cosine is a half and the sine is plus root 3 over 2, we know it's 60 degrees. And we can visualize our unit circle again and think about, well, what kind of angle would give us a cosine of a half and a sine of minus root 3 over 2? And that would be like, the full circle, 2 pi minus 60 degrees or pi over 3 radians. So what we're thinking about is full circle, 360 degrees minus 60, or full circle, 2 pi minus pi over 3 radians. And 2 pi minus pi over 3 is equal to 5 pi over 3 radians. And that's the answer. Okay, so again, go back to our earlier exercises on the unit circle, and it'll help you remember how to do this if you're not too sure about this. But you kind of have to visualize it in your head. So our answer on this occasion, the argument is 5 pi over 3 radians. So our answer is V is modulus is 4, open brackets cosine 5 pi over 3 plus I sine 5 pi over 3 radians. Okay, I hope you got something similar to that, or I hope you got that exactly. I just want to look at the marking scheme for 2 seconds for this question. So this question, I suppose, quite a simple question. The maximum points for it were 5, and I like to tell students that a general rule for telling you how long you should be spending on a question is to take the marks and divide it by 2. So for a question like this in the exam, you will have approximately 2 to 3 minutes to do this. Okay, and you know, it isn't huge. You can see how much writing is actually here. So it's a question of just knowing what you're doing and getting it down on paper as as quickly as possible, but still completing all the moves correctly. And the other thing I wanted to show you about this was the points. So the points can be awarded 0, 2, 3, or 5. 2 is a low partial credit, and 3 is a high partial credit. So for if you were able to, within this, if you were able to get the modulus or the argument, you are going to get 3 out of 5. So for example, you had 3 out of 5 by the time you were here. You had the modulus already got. So if you can imagine 3 points out of 5 for just doing this piece of the solution, which is not bad at all. Of course, you needed to get all of it right to get 5 out of 5, and that's where I'm saying in particular along here. It's if you're doing your best and going as quickly as possible on the day of the exam, maybe a little bit stressed. This is often where people make simple arithmetic mistakes. So do an extra line of maths if needs be, and get the answer right here. Do not make simple arithmetic mistakes. And then finally, just your knowledge of the unit circle and the maths tables to get the argument here. Okay. So let's take a look at De Moivre's theorem or equation for complex numbers. So basically, De Moivre's equation looks like this. A complex number z to the power of n can be represented like this. The modulus to the power of n, open brackets, cosine n times the argument plus I sine n times the argument. So it's not a very difficult equation, but just in case you're worried that you may not remember it going into the exam, it is actually included on page 20 of your maths tables in this format. So just be aware that it is in the maths tables. There's no need to learn it off, but it is not a very, very difficult equation. Just to remind you that the complex numbers have to be in polar form to allow you to apply De Moivre's theorem. Okay, so there are 2 basic kinds of questions that could come up in the exam relating to De Moivre's theorem. The first one is resolving complex binomial expansions, or binomial expansions of complex numbers. So an example of this might be z is equal to 2 root 3 minus 2i. Find z to the power of 6. The second kind of example is resolving complex roots. So you'll be given something like z to the power of 3 is equal to 8. Find z, which is the cube root of z to the power of 3. So let's take a look at both of those examples. Okay, so the first type of question that we look at using De Moivre's theorem is the resolving of complex binomial expansions, or binomial expansions of complex numbers. Okay, and this is a 3-step process. Step 1, which we did earlier, is to convert complex numbers from Cartesian to polar form. And once we have the complex number in polar form, then we apply the Moivre's theorem or equation, which is on page, I think it's on page 20 of the maths tables. And then finally, we take what we get out of step 2 and we change that back from polar to Cartesian form. So the example we're going to take is z is equal to 2 root 3 minus 2i, and we've been asked to find z to the power of 6. So step 1 of the process, we need to convert from Cartesian to polar form. We did this earlier, and this step has 3 steps within it. Step 1 of that is to use Pythagoras to get the modulus of the complex number. The modulus is written with z and a bar either side of it, and we just use Pythagoras to get this value. So we square 2 root 3 and 2, and then get the square root of all that, and that gives us a modulus of 4. The second step in the process then is to take the modulus outside of the brackets, as I like to say. So basically, we take what we got here for the modulus, put it outside the brackets, and for each element of the complex number, then divide by whatever is the modulus outside the brackets. So we get 4 open brackets, 2 root 3 over 4 minus 2 over 4i. Cancelling these, we get 4 open brackets, root 3 over 2 minus 1 over 2i. And what we have now inside the brackets really is in kind of unit circle form. Okay, and then we use this and the table on page 13 of your maths tables to find the argument of the complex number. So we have here a complex number with an argument whose cosine is root 3 over 2 and whose sine is minus 1 over 2. So start with the cosine, look along the cosine row for root 3 over 2. We've got it here, and sine 1 over 2. Yeah, so we have an angle pi over 6 whose cosine is plus root 3 over 2 and whose sine is plus 1 over 2. Our complex number here is minus a half. So what we can, from our knowledge of the unit circle, what we can say is that with cosine being positive and sine being negative, it's in the fourth quadrant of the unit circle, or the southeast corner, or the bottom right quadrant, whichever way we want to look at it. And what we can say about it is, well, where the sine is plus a half, the angle gives us pi over 6 radians. So where the sine would be minus a half, that would give us an angle which is equal to 2 pi minus pi over 6 radians, which is like 11 pi over 6 radians. It's pi over 6 off of 2 pi radians. Okay, so that gives us our complex number in polar form, which is equal to 4 over cosine 11 pi over 6 plus I sine pi over 6. Watch the change of from negative to positive here. Okay, so that's step 1 of this process done. Second step is to apply de Moivre's theorem to what we have here. So de Moivre's theorem is on page 20 of your maths tables, and it basically is that any complex number z to the power of n is equal to the modulus to the power of n by cosine n times the argument plus I sine n times the argument. Okay, so in this case we're looking for z to the power of 6, so we just substitute in 6 for n into this equation, and we get this. Okay, so z to the power of 6 is 4 to the power of 6 cosine 6 times pi 11 pi over 6 plus I sine 6 11 pi over 6, and just multiplying some stuff out. Well, 4 to the power of 6 is 4096, and then inside the brackets cosine 11 pi plus I sine 11 pi. So let me just talk about this 11 pi thing for a minute here. I want to go back to the unit circle here. So let's remind ourselves a little bit about the unit circle. So we saw earlier on, an angle of pi is 1 semicircle, 180 degrees. Okay, so that's pi. Okay, and then if we carry it on, 3 pi over 2, and by the time we get to the beginning again, now we have gone around 1 revolution, and that is an angle of 2 pi. Okay, so that's 1 revolution. Now, if we'd carried on to 3 pi, we would start here, go all the way around, and keep going back to here. That would be 3 pi. And you'll notice that basically the angle 3 pi is the same as the angle pi, isn't it? So basically what we're saying is that we can kind of ignore full revolutions of the unit circle, in that the value of cosine or sine of 3 pi is the same as the cosine or sine of pi. Keep going again, so we can imagine an angle where we start here and 1 revolution, that's 2 pi. Another revolution, that's 4 pi. And now keep going again to 1 more pi, now 5 pi. So in this, we're after doing 2 full revolutions and pi radians. So again, what I'm just trying to show you is that cosine of 5 pi is exactly the same as cosine of pi. Sine of 5 pi is the same as sine of pi, and so on and so forth. So what we need to be able to recognize is that when we have asked to find sine and cosine of angles greater than 1 full revolution, or greater than 2 pi, we can make life easier for ourselves by eliminating the full revolutions from the argument. So full revolutions are units of 2 pi. So in this case, we were being asked to find cosine and sine of 11 pi. So we can, 1 revolution is 2 pi, 2 revolutions is 4 pi, 3 revolutions is 6 pi, 4 revolutions is 8 pi, 5 revolutions is 10 pi. So we can actually just strip out 10 pi out of this and this, and it'll be the same value. Okay, so that would give us basically stripping out, taking 10 pi out from 11 pi, we're left with just pi. Okay, so our answer from step 2 is 4096 open brackets cosine pi plus I sine pi. Now, what we just talked about there, stripping out full revolutions, is something that we'll also be looking at in the next session, so worth remembering. Okay, the final step of this process then is the easy bit, really. It's converting from whatever we get from step 2 back from polar to Cartesian form. This is very simple. We just again use our tables to find on page 13 to find what is the value of cosine pi, and that is -1, and what is the value of sine pi, and that is 0, and simply multiplying it out. So we get an answer, z to the power of 6 is equal to -4096. Now, if we weren't talking about complex numbers, we'd be getting a little bit worried about this, because we know that, you know, in general maths, normal algebra, anything to be squared is always positive. So, you know, you could say that z to the power of 6 is z to the power 2 by z to the power 2 by z to the power 2, and therefore we would not normally expect z to the power of 6 to give us a negative answer. But don't forget, we're dealing with complex numbers. Okay. So the second kind of problem that might be asked to solve using the Moivre's theorem is resolving complex roots, getting roots of a complex number. Now, in the first example, where we were asked to resolve binomial expansions of complex numbers, I've never seen a question come up where you will be explicitly asked to solve binomial expansion of complex numbers using the Moivre's theorem. I've never seen that come up as a question. More often than not, if it comes up, you will be asked, maybe you'll have a complex number and they will ask you to find, you know, as in the case with the first example we did, z to the power of 6, but they won't explicitly mention using the Moivre's theorem as the means to do that. And if that does come up, of course, there will probably be points awarded for recognizing that it should be the Moivre's theorem that you use, and in that case, make sure you get down on your paper that you intended to use the Moivre's theorem. Write down the formula from the maths tables on page 20 or whatever. Now, in this case, the complex roots is very often the case that they will suggest that using the Myers theorem or otherwise resolve this problem. So the example we're going to look at here is z to the power of 3 is equal to 8. Find z. So z is the cube root of z to the power of 3. So look, there are 6 steps to this. Let's go through them one by one. So step 1 is to let w equal z to the power of 3, and we'll see this just is more convenient. We'll see that in a few minutes for feeding this back into the Myers theorem. So we have w is equal to 8, but we need to write it in complex number form. So w is equal to 8 plus 0i. Okay. And then we need to convert w to polar form, and we've gone through examples of this before, so we don't need to do that again. So it's what we end up is that w is 8 cosine 0 plus I sine 0. Step 2 done. So far, so good. Step 3 is to write w in general polar form. I haven't mentioned this before, but I kind of alluded to it in the last example. So general polar form looks like this, where you have, w is equal to the modulus times cosine the argument plus 2 pi n plus I sine and the argument plus 2 pi n. I remember what we talked about in the last example. 2 pi is a full revolution, and n is a number of those revolutions. So what we have here is cosine of the argument plus 1 or more revolutions, and we know that cosine of 0 is the same as cosine of 0 plus 2 pi. Cosine of 0 is the same as cosine of 0 plus 2 pi by 2 revolutions, 2 pi by 3 revolutions. So this is n, where n is the number of revolutions going around the unit circle. Okay, so this is called the general polar form. Now, rewriting this gives us w is equal to 8 plus cosine 2 pi n plus I sine 2 pi n. Okay. One note I want to add here: the convention for the general polar form is like this, with n in it. And unfortunately, the convention for the Myers theorem also uses n as the power of the complex number. Z to the power of n is equal to r to the power of n plus cosine n theta and I sine theta. They're not the same n, not the same thing, so don't get them mixed up, okay? Step 4 in the process is to apply the Moivre to this complex number, and the power that we're going to apply is 1 over 3. That's the cube root. So the power is a third, which is the cube root. And applying the Moivre's theorem to this complex number, we get z, which is equal to w to the power of a third. And apply the Moivre, 8 to the power of a third, cosine a third, 2 pi n plus I sine 2 pi n. That's the end of step 4. Steps 5 and 6 are a little bit longer, so we'll go on to another slide. So from step 4, we had that the cube root of w was 8 to the power of a third, cosine 1/3, 2 pi n, plus I sine a third, 2 pi n. Step 5 then is to apply values for n, the number of revolutions in the general polar form. So we need to apply values for n as required. Okay, so if we're looking for, if the question was to get the square root of a complex number, we'd be looking for 2 roots. So we would give n 2 possible values, 0 and 1. If we're being asked for a cube root, we would have 3 possible answers. So we need to assign values to n of 0, 1, and 2. And we will apply these values in turn to this formula and get 3 different answers. So let's start. So the first one, n equals 0. So feeding n equals 0 into this formula, we have, well, 8 to the power of a third is always 2. Cosine 1 over 3, 2 pi 0, plus I sine a third, 2 pi 0. And that gives us, when you multiply it out, 2 by cosine 0 plus I sine 0. So that's when n equals 0. And we have to do 2 more, substituting in n equals 1 and n equals 2. So when n equals 1, z is equal to 2 cosine a third 2 pi 1 plus I sine a third 2 pi 1. And that gives us 2 cosine 2 pi over 3 plus I sine 2 pi over 3. 2 pi over 3. That's the second root. And the last root in step 5, we assign a value of n equals 2. So we get z equals 2 cosine 2, open brackets, cosine a third 2 pi by 2 plus I sine a third 2 pi by 2. And it gives us 2 cosine 4 pi over 3 plus I sine 4 pi over 3. So that's the end of step 5. One more step. Step 6 then is to convert these factors, which are all in polar form, back to Cartesian form again. Okay, so taking each factor in turn, where z is equal to 2 cosine 0 plus I sine 0, converting that back to Cartesian gives us z equals 2 plus 0i, or z equals 2. The second one, when n equals 1, we simply convert this back to Cartesian to get minus 1 plus root 3i. And you can see again how our knowledge of the unit circle and the tables on page 13 helps us to do this. So, 2 pi over 3, that's like pi minus pi over 3, or 2 pi's over 3, and yeah, so it is in the second quadrant, so the cosine value has to be negative and the sine value has to be positive. Okay, so again, our knowledge of the unit circle and use of that table comes in again, which is great. And then finally, last one, cosine 4 pi over 3, I sine 5 over pi, I sine 4 pi over 3. Again, our knowledge of the unit circle, 4 pi over 3 is in the third quadrant, or the lower left quadrant. And so both cosine and sine will be negative. So we get z is equal to minus 1 minus root 3i. So those are our 3 roots that we were looking for. So it's a complicated enough procedure, 6 steps. It is definitely something, one of the ones I would be putting down on my checklist to remember what are the 6 steps, for example, and on my summary sheet for complex numbers using the Moivre's theorem. Okay. Okay, that wraps up our discussion about complex numbers polar form. I hope it has helped you in some small way. And now let's take another 5-minute break and meet back here in 5 more minutes to start the topic of trigonometry 3. Okay, welcome back. Let's move on now and we will look at the topic of trigonometry 3. So trigonometry 3, questions from this section tend to be, well, they're always on paper too, and they tend to be the short questions. That's the skills first half of the paper, whereas the kind of questions that you get from trigonometry 1 and 2 would tend to be the applications, long questions, second half of the paper on paper 2. So there's quite a few topics to cover under trigonometry 3. They include 2 common simple problems that seem to come up again and again and again in the short questions for trigonometry, and I think it's worth covering both of those just in case they come up again. And then we're on to a kind of a wider topic of trigonometric equations, and there are a number of parts to this. First of all, there is just a review of all the equations that are on the course, 24 in total, 9 of which have to be proved. You need to may need to be proved, may be asked to be proved, and you need to know which ones proofs may be required for in the exam and be able to do those. And then there's the more general manipulation of trigonometric equations to express something as a sum, a difference, or a product, and we look at 1 or 2 examples of those. Next, then there's trigonometric identities. That's using your trigonometric equations to prove that something equals something else. So it's about converting something in one form to something in another form using the trigonometric 24 trigonometric formulae in your maths tables. There is compound angles and double angles, so equations relating to those. And then two obscure, more obscure kind of topics or subtopics. One is inverse trigonometric functions, and then finally trigonometric limits, which again I've really never seen come up, but it's worth covering. There are two relatively simple trigonometric problems that come up again and again commonly on papers over the years. So it's worth taking a look at both of these and make sure that we're very familiar with them in case they happen to come up again next summer. The first kind of problem looks something like this, where we're asked to solve for cosine 3 theta equals 1 over root 2, and the answer will be given in very specific values, a number of specific values for theta. For theta would be in a range defined here between 0 and 360 or 0 and 2 pi radians, and take special note of the range involved, whether it includes 360 or not. The second type of problem looks something like this, where it's again very similar, but and again cosine theta is equal to minus a half. Theta is again in radians, but in this case the solution would be in kind of a general solution form for theta, and we'll see what that looks like in a minute. So both of these examples requires a good knowledge of the unit circle, as has most of what we've done so far. So let's take a look at the first example. Solve for cosine 3 theta equals 1 over root 2, where theta is between 0 and 360 degrees. So given that they have mentioned the range in degrees, it looks like they want us to work in degrees and perhaps give our answer in degrees in this occasion. Take special note of the range. Theta is greater than or equal to 0. Theta is less than or equal to 360. Okay, so step one, and this is a three-step process. Step one in the process, we've done a number of times now already today, is to find the reference angles for 3 theta, angle for 3 theta. Okay, and we will once again use our table on page 13 of the maths tables. Okay, always a good idea to draw a unit circle in for these type of problems. Okay, it'll as we've seen so often before, it can help us understand what we're looking at somewhat better. So we know that 3 theta is equal to a half. Cosine 3 theta is equal to 1 over root 2. So we, using our table, we look along the cosine row for 1 over root 2, and we find it here. And on this occasion, we're working in degrees, so we can see that we have an angle of 45 degrees. So we know that one of the possible answers for cosine 3 theta is 45 degrees. And we see it here. But looking at our unit circle, we can see that there is another angle, which is down here, which also has a cosine of 1 over root 2. 1 over root 2 is the horizontal distance along the x-axis here. Okay, so it gives us an angle of 45 degrees. But if you look at the unit circle, you can see that there's a second solution for 3 theta, which is 360 degrees minus 45 degrees, which is 315 degrees. Okay, so we have two possible solutions then now for 3 theta, which is 45 degrees and 315 degrees. So that's the end of step one. Next step then is to take what we've got in step one and add a number of full revolutions. Okay, so we started out with 45 and 315 from step one, and to each of these we're going to add 1, 2, 3 revolutions, a number of them. We'll go on for maybe 3 revolutions. Okay, so 45 plus 1 revolution is 360. 315 plus 1 revolution is 315 plus 360. 45 and 2 revolutions. 315 and 2 revolutions. 45 and 3 revolutions. 315 and 3 revolutions. And just doing the maths on those and converting them to degrees, this is what we get for 3 theta. So we have 1, 2, 3, 4, 5, 6, 8 solutions for 3 theta here, and it may or may not be necessary to go on. You don't really know how far you need to go on until the next step, but you, generally speaking, 3 revolutions seems to be enough. Okay, so that's the end of step 2. So now we have solutions for 3 theta. Step 3 then is simply to find solutions for theta. So if theta is 45 degrees, 3 theta is 45 degrees, theta is 15 degrees, simply dividing each of these by 3. 405 divided by 3, 135. 675 divided by 3, 225, and so on. And we went on for each of these solutions of 3 theta to give us a solution for theta. Okay, not quite there yet. However, reading the question, we were asked for solutions for theta between 0 and 360 degrees. So if you look at what we've got here, we have from 15, 105, 135, 225, 255, 345, 375. That's outside of the range that we were asked for. So our answer will be 15 degrees, 105, 135, 225, and 345 degrees. Make sure you read the question properly and give them exactly the answer they want. This will get you very, very high attempt marks, but I would be a little bit worried that if you included 375 and 465, that you might not get exactly give exactly the answer to the question they asked and deduct marks unnecessarily, because you have all the work done by the time you get to here, and all you have to do is just read the question again and just give the values for theta in the range that they asked for. And again, be careful. Just look at whether you're. It doesn't matter on this occasion, but it can sometimes matter whether you're being asked for a range where theta is less than 360 or less than and equal to 360. So make sure you take note of that. Okay, that's the first one done. The second kind of problem that we can get is very, very similar. In this case, we will be looking for an answer for theta in radians. That doesn't really matter, but the solution will be in the form of a general solution rather than specific values for theta. So let's go through it. It's actually a simpler process. There's only 2 steps in this. So step 1, as in the last example, is to find the reference angle. Okay, and once again we will be using our friend the table in page 13 of our maths tables. And it's always a great idea to draw a unit circle for these type of questions. So let's do that. So the question we have is to solve for cosine theta equals minus 1/2, 1 minus a half. Okay, so using our table, we look for a value where cosine theta equals a half, and we can look again, go along the cosine row, find that value, and let us know what that gives us. So that gives us an angle of pi over 3 radians, or 60 degrees, which would be this kind of angle here on our unit circle. But we weren't asked for cosine theta equals plus a half. We were asked for cosine theta equals minus a half. So cosine is along the horizontal axis, so we look for angles where cosine theta equals minus a half. That would be around here, and that gives us an angle here and here. Now we know that plus a half gives us an angle of pi over 3, so we can use our knowledge of the unit circle to imagine what this angle must be. So it's like pi minus pi over 3, or down here it's like pi plus pi over 3. So I lifted this specific example from a textbook, and the textbook is basically saying the same thing. Use your table here to find the positive angle, which would be pi over 3, but now it's in the negative cosine areas. So imagine an angle that is pi minus pi over 3, which is 2 pi over 3, or an angle which is pi plus pi over 3, which is 4 pi over 3. But either way, however you want to imagine it, you will end up with solutions for theta that are 2 pi over 3 or 4 pi over 3. So that's step 1. Step 2 is simply to convert that into a general form. So you don't necessarily need to write this down as part of your solution, but basically what you need to do for each of these two angles is to add n revolutions. Okay, so again, the example lifted from the textbook I took, they're saying that with every full revolution, the same ratio is given. So taking 4 pi over 3, cosine of 4 pi over 3 is the same as cosine 4 pi over 3 plus 1 revolution, which is 2 pi, which is the same as 4 pi over 3 plus 2 revolutions, etc., etc., etc. So writing this in general form for both 2 pi over 3 or 4 pi over 3, the answer we get is theta equals 2 pi over 3 plus 2n pi, where n is an integer denoting a number of revolutions, or theta is equal to 4 pi over 3 plus 2n pi. Okay, that completes the first part of our trigonometry 3 session. That's the two common and simple problems that seem to come up again and again on exam papers. So definitely well worth looking at and keeping in mind. So let's move on to something a little bit more difficult. That's trigonometric equations. To a large extent, trigonometry 3 is about working with trigonometric equations or formulae. And I've lifted this image from one of the revision books that I like to use. I think it's Revise Wise or Less Stress, More Success, something like that. And it lists all the trigonometric equations on the course. There are 24 in total. And you need to be able to prove 8 of them. Those are the ones with the asterisks marked here. Okay, so I'm not going to go through the proof of these formulas today. They are all detailed in your textbook, and what I would suggest is, in the first instance, look at the proofs in your textbook and understand them. And then I would maybe take a copy of those 8 proofs and keep them in a kind of a maths notes folder where you can lay your hand on them very easily. You know, in the days and weeks prior to an exam, and then is the time really to be committing these proofs to memory. Committing them to memory and learning them off by heart now might be somewhat a waste of time, because you'll have to have forgotten long before the exam arrives. Right now, you just need to make sure A, you understand what the 8 proofs you need to be able to perform are, understand those proofs, and have a copy of them to hand in in your maths revision folder, so that when the time comes, maybe starting 1-2 weeks before the exam, start to learn them off by heart and test yourself on those. Learning proofs can be a relatively easy way to gain marks if the proofs come up. Okay. So I want to say that when Department of Education people are setting exams, their job is to set a certain number of questions that any student could reasonably be expected to answer, and then setting other questions maybe that not every student could reasonably be expected to answer, maybe a smaller proportion, and then a few questions, I suppose, that only maybe the very strongest and brightest students might be reasonably expected to answer, and that's the nature of the exam. And I have to say that my feeling is that this area would tend to be one of the more difficult areas for most students on the course. And I certainly worked with a number of students who would take one look at this list of equations and say, nope, not for me, can't do that. But what I hope to do is to give you some guidance and some maybe rules or structure that will help you navigate your way through this list of equations, and hopefully will give you some tools that you can use in an exam situation answering questions to figure out what is the specific equation that you should be using for the question at hand. And if we get nothing else out of today on this topic, it would be great if we could achieve that. So I think that list we saw on the last slide was kind of scary. All those formulas just in one big long list. And in a minute, we're going to look at some simple Trig 3 problems using some of those formulas. But before we do that, I want to take you to your good friend, the maths tables, and let's see what we have in there. And the good news is that actually all 24 of those trigonometric equations are listed in your maths tables that you will be bringing into the exam hall with you. To a large extent, they're on page 14 and 15 with a couple of them on page 16. But what I want to really draw your attention to is how they're organized and arranged in your maths tables. They're arranged by function, I suppose, by job. In other words, similar equations that do the same job are listed in each section. So let's just go through the four sections in page 14 and 15 and really understand what it is that the equations in each section are supposed to do. So then hopefully when we get a problem to do, and we can understand what exactly we're being asked for, we can go quickly to the appropriate section and pick the appropriate equation out of the appropriate section. So two sections on page 14, the compound angles and the double angles equations. So you might remember from your junior cert science, a compound is a substance made up of two or more elements, I think, if I remember correctly. So compound angle formula are made up of two or more angles. Okay, so it can, we call them A and B, and it can be we can be looking at adding the two angles or subtracting the two angles, but basically what we're talking about is equations which involves two or more angles. That's the compound angle formula. Okay, somewhat similar but not quite the same is where we're dealing with equations where we're doubling angles. So you have an angle A and we're looking at 2 times that. Okay, and there are six equations relating to compound angles, 7 equations relating to double angles. So that's 13 of the 24 on this page alone. And again, if you can recognize from the question that you're dealing with a question that requires the manipulation of 2 different angles, the appropriate equation is probably in this section. Or if you're doubling up one single angle, then this is the section you need to be looking at. There are 2 more sections then on page 15. They are the products to sums or products to differences equations. And a product is when you multiply 2 things together. So cosine A by cosine B, for example. And so that's a product when you're multiplying 2 things together. And that could be taking a product and making a sum out of it, so cosine something plus cosine something, or making a difference out of it, cosine something minus cosine something. So this section gives us the products to sums or differences section. Okay. The opposite, sums and differences to products, is down here. And I mean, you could work your way from here to these, but why bother? It's already done out for you in detail here. So all you got to do is look at your question, understand what you're being asked, and if it is the case that you're being asked to translate a sum or a product of 2 different sine or cosine to product, then this is the section you need to go to. So we have 13 here, further 8 here, so that's 21 in total. The remaining 3 are, well, the sine and the cosine rule are on page 16, and I think the very first formula we looked at then is back back on page 13. But for Trig 3 purposes and the manipulation of trigonometric equations, these two pages are really where it's all at. So we're going to take some simple examples of trigonometric questions and work through them using the pages from the maths tables that we just looked at. Okay, so these are some questions that were created by my predecessor who was previously delivering this module. So the question we're going to attempt first is express as a sum or difference cosine 3x sine 4x. Okay, now the first thing that my predecessor suggested in these kind of problems is always write the larger angle first, and which avoids a negative angle in the answer, which makes sense to me. So this would certainly be one of the tips that you might like to put in your summary sheet or your check sheet for this chapter. Okay, so let's do as he suggests. So we just rewrite cosine 3x sine 4x to sine 4x cosine 3x. And we'll see later on why that becomes a good idea. Okay. So what is it we're trying to do now? Again, as I mentioned, I've certainly worked with students in the past who would look at this kind of question, express sine 4x cosine 3x as a sum or difference, and really literally would not know where to start. Okay, and what I just, if we achieve nothing else, what I want to be able to do is give you the tools and knowledge to know where to start, so that you will probably be able to identify the equation from the log tables that you need to work this out. And in these kind of problems, identifying the correct equation from the maths tables will carry low to medium attempt marks. Just writing down the equation that you would need to use to solve this from the maths tables will get you low to medium attempt marks, nothing else. But of course, identifying the right equation will also help you get the right answer and possibly full marks for this question. Okay, so let's see what we're dealing with here. So we have sine 4x by cosine 3x. So they're multiplied by, so this is a product. And what we need to do is convert this product into a sum or difference. Okay, so we need to go to the products to sum and differences section of page 15 on your maths tables. Okay, and there are 4 equations here. And simply all we need to do is look at this and decide from here which of these 4 is the correct equation to use. So we want sine by cosine. So sine by cosine. So it's actually the second equation. 2 sine A cosine B is equal to blah blah blah. So okay. So let's write this down. So using formula, and I literally all I've done is rewrite the formula from the maths tables as my starting point. I'm already on the points board here. I'm getting low to medium already. I've shown the examiner that I understand the equation that I should use, and if I do nothing else, or if I make an arithmetic error after this, I've already got points for this question. With quite little effort, just taking a minute or two to think, what am I being asked, and going to my maths tables. Okay, now that I've identified the correct equation to use, it's just a matter of filling in for A and B. Okay, so in this case, A is 4x and B is 3x. Okay, so I've done my predecessor has done a few steps in one here. He's taken the 2 over to this side. That's my half there. So what he's put in is his A is 4x and B is 3x. So sine 4x cosine 3x is equal to half, open brackets, and then sine A plus B, 4x plus 3x, plus sine 4x minus 3x. And then it's just a matter of completing the arithmetic, and there's our answer. So, I guess it is likely that small or simple arithmetic errors can be made in this one, but getting from here to here, but simply getting the correct equation at the beginning is more than half the battle on this one. Okay, next question. Express as a product, cosine 4x and cos 2x. So what is it we're trying to do here? We have an addition or a sum, and we're trying to change it into a product. So we need the section sums and differences to products. Okay, so we go to that section, and we see there are 4 equations, and we need to pick the correct equation out of this section relating to this problem. So it's cosine plus cosine. So we need to find an example where you're summing or adding cosine plus cosine. So we see it's the first equation. Okay, and again, if you do nothing else, if you're running out of time and you do nothing else for this question, write down the formula from your log table, which you have in front of you, onto your exam paper, and you are on the scoreboard immediately. Okay, so get that right first, and you have half the battle. More. So now that you have that down, it can be useful to so that you know to avoid making silly arithmetic mistakes. Write down which is A and which is B. It just helps a little bit. So in this case, A is 4x and B is 2x. So just substituting in then for A and B. Cos 4x plus cos 2x is equal to 2 cos, open brackets, 4x plus 2x all over 2, multiplied by cos 4x minus 2x all over 2. And that ends up very simply being 2 cos 3x multiplied by cos x. Job done. So that was just a couple of perhaps maybe relatively simple examples of problems using the formula on page 15, which are the trig equations from sum difference to product, or from product to sum or difference. So let's look at the next group, which are on page 14. They're compound angles. That's when we have 2 different angles, A and B, or double twice the same angle to A. Let's take a few examples and look at those. So let's look at an example of a question looking at compound angles using trigonometric equations. So this is, A plus, where you have 2 different angles, A plus B, or twice an angle. Okay, and the example I picked is this one. Express cosine 75 degrees in third form. Now you'll remember that third form is an expression using square roots or cube roots or something like that. Okay, so unlike the last 2 examples I did, this question is not instantly recognizable as a trig equation problem for compound angles, and your suspicion should initially be aroused by the fact that we are asked to find cosine of 75 degrees. Now, you will remember it's a strange angle. You'll remember that we talked earlier about, in these kind of topics, we predominantly deal with 16 angles of interest, I think I call them. And they are, 0, 30, 45, 60, 90, 120, 135, 50, 150, and so on. Actually, there's 17 angles here, but 0 and 360 are essentially the same angle. Okay, and so it would be strange for us to be asked to do something with 75 degrees. And of course, the clue is, or the key to this question is that we need to represent 75 degrees as some kind of compound or combination of 2 different angles from this list. And once we do that, then we're talking about an A plus B, and we can treat it as a trigonometric equation problem with using compound angles. Okay, now I am sure that you can think of many combinations of these, of adding or subtracting 2 angles from this list to give you 75, but I'm going to pick the simplest possible combination of these angles. So I'm going to use 75 degrees is equal to 45 degrees plus 30 degrees. So now we're in a situation where we want to find a cosine of an addition of 2 different angles, 45 degrees and 30 degrees. Okay. So we go to page 14 of our log tables and we see, well, okay, which equation in the compound angle formula section can we use for this purpose? So we're looking for cosine of a plus b, and this is our equation here. So let's write that down, and the minute we write that down on our exam paper, we are already on the scoreboard as far as the examiner is concerned. Okay, so it's always a good idea to help us to avoid making sloppy arithmetic mistakes by just write down which is A and which is B, and that'll help us substitute into the equation correctly. Make sure we don't make any mistakes there. So what we end up with then is cosine of 75 degrees is equal to, using this formula from the maths tables, cosine 45 degrees by cosine 30 degrees minus sine 45 degrees by sine 30 degrees. So what next? Okay, we go back to our friend, the maths tables again, page 13 this time, and we have our table. We have the table of all our angles of interest, or most of our angles of interest, with corresponding sines and cosines for them, and we simply substitute for the cosine and sine values here from here, taking these values in this table. Okay, so what we get from that is cosine 45 degrees. Cosine 45 degrees is 1 over root 2. There it is. Cosine 30 degrees. Cosine 30 degrees. Root 3 over 2 there. And similarly, sine 45 degrees. 1 over root 2 by sine 30 degrees half. So we end up with this, which is a collection of surds, which is what we want to get out of all of this. So just multiplying each term, we get something like this, which is root 3 over 2 root 2 minus 1 over 2 root 2. And because we have a common denominator, we can combine those into root 3 minus 1 over 2 root 2. And I would be perfectly happy with that as a final answer for this question, but in the example I took out of the book I took, they have made one more step, not sure why. They multiplied above and below by root 2 to give us root 6 minus root 2 all over 4. Okay, that is a great example. It's somewhat more difficult than the examples, the initial two examples we did for the sum difference products, but this is somewhat more difficult, and it is the kind of standard that you can expect on the day. So that was a really good example of a compound angles problem. Let's move on to trigonometric identities, and basically these are concerned with proving something equals something else. So trigonometric identities are basically about proving something equals something else. Okay, so it involves proving some trigonometric expression on the left hand side equals some trig expression on the right hand side. And to do this, we will use one or more of the 24 trig formula in pages 14, 15, 16 of our tables, but you have to figure out which ones it is we should be using. Now, this can be a difficult topic. We are certainly getting into more difficult territory with these kind of problems. It may well be the case that you've never seen a question like this in your class or your homework over the senior cycle, and you're seeing something like this for the first time, and it might require some creative thinking and or some or a lot of luck if you are going to find the or a path that will take you to the solution. To be good at this really takes a lot of practice and experience, okay? And from a revision point of view, I would suggest when you're doing this chapter in class, as you go through examples of different kinds of this problem, keep 8 or 10 of them as examples, worked out examples, and photocopy them and put them into your revision notes or folder, and then refer to these as as examples each time you revise this chapter. A tip that I got from one of the revision books that I got was generally it's advised to start with the more complicated side of the equation and use your formula on page 13 to 16 to manipulate the expression until it equals the opposite side of the equation. So let's take an example of a trig identities problem. The example I'm going to take is prove that the square root of 1 minus cosine 2a all over 1 plus cosine 2a equals tan of a. Okay, so taking our advice from the last slide, I'm going to start with the more complicated side, which is the left-hand side in this case. So the left-hand side is equal to the square root of 1 minus 2 cosine 2a all over 1 plus cosine 2a. So I'm noticing that we have this the double angle thing here, cosine 2a here. So I'm going to take a chance that the approach that we should take is to use one of the double angle formula from our table. So it's we're dealing with cosine. So the formula I'm going to use is cosine 2a is equal to cosine squared a minus sine squared a. Now, write that down on your paper. If it is a step in the correct direction or in the right path, you are on the scoreboard already. Okay, so don't lose out on those vital points by showing evidence that you intend to use this formula. Okay, so applying this formula into this, I substitute cos 2a for cosine squared a minus sine squared a. So I have it here and I have it here. Okay. That's fairly simple. Next step, I'm just multiplying out these brackets. So what I end up getting is 1 minus cosine squared a plus sine squared a, and I just have brackets around it here because I'm preparing for the next step. Actually, the very first trig equation on the list is on page 13, which is that cosine squared a plus sine squared a is equal to 1. So I'm going to substitute in cosine squared a plus sine squared a for 1 in this equation. And if I do that, I end up with cosine squared a plus sine squared a minus cosine squared a. So that leaves us with sine squared a for this. So instead of this, I get sine squared a. And similarly below the line, instead of 1 minus sine squared a, I get cosine squared a. So now I have square root of sine squared a plus sine squared a all over cosine squared a plus cosine squared a. And that's very simply equal to 2 sine squared a over 2 cosine squared a. And of course the 2's cancel. And tan is equal to sine over cosine. So we can say that this is equal to root tan squared a. And root tan squared a is simply tan a, which is equal to the right-hand side, which is what we were asked to prove. Okay, so what can we say about that? It is definitely quite a long way over on the more difficult side of the spectrum of kind of questions that would be asked to solve in the exam. I would say the vast majority of students would not be able to do that in the time allocated in an exam situation unless they had previously seen this example or a very, very similar example. And that's why I'm saying that for questions of this difficulty level, really, it is the students who have most experience and practice in doing these kind of questions and have semi-committed to memory methods or paths or solutions for doing these that will be able to do them in the time allocated and that you have available to you in exam situations. So I guess as a general rule, I would suggest if this is perhaps not your forte, um, at least make an attempt at it, an intelligent attempt to start the question by looking at, taking the more complicated side and guessing what the first step might be by, in this case it was the double angle one, it could be the compound angle one equation or something like that, and write the equation down so you get onto the scoreboard at least. Whether or not you negotiate your way through the other steps to the solution at the end, well, I'm afraid it takes quite a bit of luck. But at least if you're on the scoreboard, you're heading in the right direction. So that concludes our discussion on trigonometry 3 and indeed our discussion on maths for today. And you might feel as if you have had enough listening to me for one day and want to sign off now, but if you have still a little bit more energy and patience, I'd like to take a few minutes to share with you some tips and ideas and advice for preparation for the Leaving Cert Higher Level Maths course that I myself have been shown or learned or developed through working with students taking the higher level Leaving Cert course over the last 6 to 8 years. Maybe these ideas are not for everybody, but even if some of you are interested in adopting some of these ideas, it may be of benefit to you over the coming months. Okay, I just want to take a few minutes now to give you some tips or ideas or advice for preparing for your Leaving Cert exam in higher level maths. But before I do that, I want to let you know about a supplement, a newspaper supplement on Leaving Cert Maths that I came across actually in 2014. Now, it's actually still online and you can find the supplement yourself online if you Google Exam Times Maths Supplement. Exam Times Maths Supplement. It's a supplement from the Irish Times and it's still available online as of at least it was today when I checked. So if you Google Exam Times Maths Online, and you should get at the top of the list a link to a folder in the irishtimes.com website, and click into that, you should see something like this. So the URL is www.irishtimes.com/sponsored/exam-times/maths, and you'll arrive on this page here. And basically, this is talking about a supplement that was written by a guy called Aidan Rowntree, and Aidan is kind of the Elvis of the Leaving Cert Maths world. He literally wrote the book. And he wrote this supplement. I thought it was very, very good. You can get it. You can get the supplement by clicking on this link, and it looks like this. And it's if you are into your maths, this is really worth having a look at. Okay, it includes a synopsis of paper 1 and paper 2. For both higher level and ordinary level maths Leaving Cert. It includes a number of articles that you might find interesting. It includes lists of do's and don'ts for students, and then some discussion topics for teachers. So well worth a read if you're into your maths. Okay. Also in there, there was an article by a young lady who had sat her Leaving Cert the year before this supplement was published, and I just want to take you through the advice she was giving students, because I think you might be more inclined to take advice from somebody who's a little bit more of your contemporary than myself. The article is called "How to Get Your A1." Now, this was in the days before H1 and H2, and as you know, H1 is, I think, is at 91 to 100%. An A1 in the day was 95 to 100%. So she's she's telling you how to get your A1 in higher level maths. So this was somebody who had done Leaving Cert just previously before, and I read this article, and let me just go through it very quickly. So read from the top. There's no doubt that honours maths is more time consuming than any other subject on the Leaving Cert Maths course. But with an extra 25 points available, it's worth an extra bit of study. At this point, the most important thing is to complete your homework every night and to make sure you understand what the teacher is covering in class. Everyone learns at a different pace, and although it's completely normal to have a mental block with certain topics, it is critical to seek help as soon as this happens. Don't wait until the week before the exam to look for help on topics that you are struggling with. Ask a teacher, friend, or a family member to explain any grey areas, and that's exactly how I got involved a lot in maths over the last few years, helping family members or children of family, of friends, or so on and so forth. It's the next bit that I really want to bring to your attention. So once you finish a topic, summarize it on one sheet of A4 paper and keep your summaries in a separate revision folder. Be sure to include definitions as part of these summaries, since they are often asked in project maths questions. I found these summaries extremely beneficial in my preparation the night before the exam, whereas a big pile of notes or a thick book would have been daunting. Okay. She goes on to say, the night before the exam, don't try to tackle different questions or exam papers. Just go over your revision folder, review your summaries, and ensure you have everything necessary for your next day. Now, I remember clearly reading this back in 2014 and recalling my own experience of the Leaving Cert, and I can remember coming towards the end of May and starting to, in that last week or two before the exams, and trying to prepare. I can remember having something like 20 foolscap copies full of 2 years worth of homework and 2 textbooks, and I can remember, trying to use my 20 maths homework copies and vaguely recalling some kind of question or something that the teacher had done at some point in the previous 2 years, and spending maybe 10 or 15 minutes going through copies trying to find it and actually forgetting what I was looking for to begin with. So the 20 foolscap maths copies ended up being completely useless, and I was basically left with just the textbooks to revise with. And I realized that if I had done something such as Ashling here has suggested, I would have been in a far better place as far as preparation for the exams are concerned. And I certainly wouldn't have been as stressed. I think the idea of having these personalized one-page summaries for each chapter is an absolutely fantastic idea, and I could quickly and easily see the benefit of this as a revision tool during the course of the 2-year cycle, but also in the 2 weeks and the 2 days and the day before exams, something to just bring to mind the bits and pieces in each topic, and because it's personalized, it means that the emphasis is on the bits and pieces that I might have particular trouble with. So reading this article really changed how I felt about preparing for and revising and studying for the Leaving Cert Maths exam. And really since then I've been mounting a one-man crusade with any student that I've worked with, trying to convince them of the value of doing these kind of summaries for themselves to aid them both in their understanding as the 2 years during the course of the 2 years, and then having something to call to mind the bits and pieces relating to the topic in the hours and days immediately before the exam. So basically all the advice I'm going to give you now, or the bits and pieces of advice I'm going to give you now, really lead on from reading this article about Ashling's experience, and I hope you find something in there that might be of use to you in your own revision over the coming months. So here now are basically the tips or pieces of advice that I have learned myself or picked up during my last 5 or 6 years journey of refamiliarization with the Leaving Cert Maths course, and through my time helping students with that exam. Number one on the list: revise, 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 or practice, practice, practice. So I don't think that's something that will be new to you. I'm sure your teacher's saying that to you all the time. Number two, make notes of each topic. So ideally, this is something as you would do as you're learning the chapter or topic in class. Just make some notes. It doesn't have to be very long. But it can take a lot of time. Now, I have noticed that some math teachers encourage students to keep a separate notes copy, separate from their homework copy. So this would be something where, maybe they would write explanations about a specific problem or solution, and maybe they would encourage students to write a specific problem into the notes copy as an example, so that separate from their homework copy, so that they would have this notes copy then as a kind of a guide to, studying the chapter, 1 year later, 2 years later, whatever. It would be great if every maths teacher encouraged their students to do that, but I did a poll in the tutorial session last year, which was held on campus in UCC, and I think about 1/3 of the students confirmed that their maths teachers had encouraged them to keep notes copies. So it looks like a majority of maths teachers don't encourage their students to keep notes copies, unfortunately. So whether or not you're encouraged to do so, I would be encouraging you to do that. Whether or not you make notes during the course of the topic, once you're finished with a topic in class or a chapter in class, I would encourage you to make a summary of that topic, and that's exactly what Ashlyn was talking about in the previous slide. So ideally, after completing the topic in class, make a 1-page, or it doesn't have to be exactly 1 page, but 1 or 2-page summary of the topic. It is tailored specifically by you for you, so it explains the bits that you had particular difficulties with in a way that you understand. We're talking about 1 to 2 pages per topic. There are 8 to 10 topics on each maths paper, so the summaries would constitute maybe 20 pages, 15 to 20 pages for each paper. Okay, and they should include, a list of the bits and pieces for each topic, what constitutes the topic, any formulas, definitely any formulas that are not in the maths tables, because you'll have to learn those off by heart, and also a list of the proofs that you might need to learn. So I wouldn't be suggesting that you would learn them early on in the senior cycle, but have a clear list of the proofs that you need to learn off by heart, and have the proofs readily to hand, so that when it comes time to those days before the exam, it's clear to you what you need to learn off by heart. Okay. It should take no more than 1 hour to create this summary for each topic, so it's not a lot of time. Again, there's only like 8 to 10 topics for each paper, so at the end of each topic, spend that hour. It can be difficult enough, but spend that hour, make the summary, and put in the time. It is worth it. You can use things like your own notes as a source of the information for your summary, or often textbooks would have at the beginning of the chapter a list of the learning outcomes. So that should agree with your summary. In other words, everything that's in the learning outcomes should be in your summary. Or I mentioned earlier on the use of revision books like Revise Wise and Less Stress, More Success. I find them quite good, just as a kind of a summarized version of each chapter. They're very handy. Or you can use the supplement that I talked about in the previous slide. Okay, so that's straight from Ashlyn's advice. Make summaries of each topic. Here's one that I made. I showed you earlier on. I'm not saying it's a good one and a bad one, but what I am saying is it is perfect for me. So you make your one for you. Okay. Next thing that idea that I've kind of created is the use of checklists. And this is something that we would use in my work. Checklists are basically, what it says in the tin, it's a list of checks that you can do. And the idea of the checklist is that it's most easily done when you have already created a summary. So you would use the summary as a starting point. And it should list the skills or subtopics that you need to know for the subject. But include a sample question and answer, and make the sample not one of the easiest ones, make it one of the more difficult ones, so that if you're able to do that particular sample, you're able to do any question that might come up in that subtopic. Okay. And this in particular you would use for periodic revision and practice and to test yourself. So, all the studies around revision and learning say that you should try to revise a topic, once every 1 month or 2 months or something like that. So this could be a tool that you would pull out maybe once a month, and spend no more than 5 or 10 minutes checking that you still understand how to solve these sample questions and answers. Here is a sample of a checklist that I've created for me. It includes things like, okay, I need to know how to convert Cartesian to polar form. And I have given myself an example here of -1 minus root 3i. And what I would do is I would pull this sheet out. I would attempt to convert -1 minus root 3i to polar form. And if I can't do it, that means I don't know the topic well, and I have to go and study a little bit more. But if I do know it, it just confirms to me that I still know how to do it, and it's all going well. The check sheet should include both the question and the answer. So in this case, I have converting to polar form and converting back to Cartesian form. So the question here is the answer here, and vice versa. So again, this is a checklist that's, I'm not going to say it's good or it's bad, but it's perfect for me, and it allows me to test my knowledge of a particular topic in a very, very short space of time. Okay. The next tip is to identify your low-hanging fruit. These are just topics that you particularly like and understand. And the reason I mention this is that depending on whether you're a H1 or a H6 student, and I know people don't like those terms, but you might have some scope to leave out stuff that you really hate. So we all know in the higher level maths course, there is no choice. There is typically 9 questions to do 9. And so if you're a H1 student or a student who is hoping to achieve a H1 in that, you have no choice but to study the entire course. You have to have good knowledge of every topic, because you have to answer every question that comes up. Now, if you're a student who's perhaps not as enthusiastic about maths, but feels maybe compelled to do the higher level maths because of the additional 25 points, then you may have some wriggle room there, and that there may be some topics that you really struggling to understand, and or that you don't like. And perhaps if there are 1 or 2 of those that you're just not able, or not don't seem to be able to get on top of, you might choose to leave those aside and concentrate on topics that you that you like more or understand better. And in that way, you can perhaps eliminate a waste of time studying stuff that you can't, that you don't understand, or won't be able to answer questions on. Just an idea. Make 2 folders, one for each maths paper, paper 1 and paper 2. And the reason I'm suggesting this is that it is so easy to mix up what topics are on paper 1 and what topics are on paper 2. I can absolutely guarantee you that somebody will walk out of your exam hall next June saying something like, wow, I never knew that complex numbers were on paper 1. The maths course is not always taught in the sequence paper 1 first and paper 2. Maths teachers often jump around topics. We saw an example of that today. Complex numbers is on paper 1, trigonometry is on paper 2. It is so easy to get them mixed up, and in the mayhem coming up to your exam on June, it would serve you very, very well to have a clear, concise statement of what topics you need to prepare in the 24 to 48 hours before the paper 1 exam, and similarly the paper 2 exam. And you can simply easily do this as you're doing your notes and your summaries and your checklist. Put them into a paper 1 folder or a paper 2 folder. Okay. And finally, make copies of any proofs that you have to learn off by heart and include them in your with your notes, summaries, and checklists in your paper 1 or paper 2 folder. Again, I think I mentioned this earlier on. You don't want there to be any confusion coming up to the 24 or 48 hours before the exam. What are the proofs that you need to learn off? Are they for the paper that's coming up, or it could be paper 1 or is it paper 2? And then, just to have the proofs there so that you can test yourself easily without trying to find them in the book or what have you. So if you do all of these things, what you have then you end up with is a separate folder dedicated to each maths paper with less than 50 pages in each folder, okay, which is a lot less daunting than a full textbook. And this is a vital resource for your May-June revision time. The folder should contain all or most of what you need to revise each paper. Do this now. Your May-June self will thank you. That's it. Okay, that concludes today's session. I would like to thank one more time CEIA for organizing and facilitating today's session, and indeed the entire program of sessions over the course of these months. And I'd also like to thank you for sticking with us for today's session. I hope that you have gotten something out of it that will be a benefit to you. The Leaving Cert is a challenging couple of years, and higher level maths in particular is particularly challenging. The best advice I can give you is, number 1, look after yourself over these months and years, and give it your best shot. And after that, what will be will be. Take care. Goodbye.